Hello and welcome to the video. Today we'll be looking at angular momentum and some problems where you should use angular momentums and another one where you shouldn't. So first, the subject we'll be using in our tracker videos. Here I have some fishing string that I tied two nuts to in order to give them some mass. And as you can see, it weighs about 20 grams and it has a length of about 30 centimeters. You can't see it clearly in this picture, but at the end there at 30 centimeters, there's a little knot, so I know where to hold onto the fishing string, and so it doesn't slip out of my fingers. So first, what is angular momentum? I feel like a lot of people usually struggle with this, and it is, well, if you know what linear momentum is, it's just mass times velocity. It is the same thing, but for rotating bodies. And if you look at the definition of it, the angular momentum is equal to the mass moment of inertia times the angular velocity, which, as you should already understand, the mass moment of inertia is the equivalent to mass in a linear system, just in a rotating system, and the angular velocity is the equivalent to velocity in an angular system, in a spinning system. So in this case, since there's a point mass, the mass moment of inertia is going to be equal to mass times radius squared. Now, if you have a rigid body, it's going to be different than this, but this is only for a point mass. And if we do some simplification, we can find that the mass moment of inertia is actually equal to mass times the radius times the speed at which the mass is spinning. So now, to begin, we're going to look at an example where angular momentum doesn't apply and you would have to use other methods to solve the problem. So let's go into tracker and look at it. So here's tracker, and as always, just let the motion play. So as you can see, the string, the nuts just spin around, and then after a few rotations, I let them go, and they continue going in the absence of a force forcing them to spin around. They keep going in a straight line and at constant velocity. So now let's go back to the slides and let's see why this doesn't abide by the conservation of angular momentum. So here is a body diagram of the situation. So you have the object spinning around, and then you let it go, and it just has a speed going in a straight line, which is going to be the same as the speed that it is spinning at. So now, if this was to abide by the law of conservation of angular/linear momentum, we would find that it has an angular momentum that is equal to the mass moment of inertia times the angular velocity, which it does have that angular momentum. But then afterwards, we would find that the angular momentum would be equal to the linear momentum, which is just mass times velocity. So what this would result in is that, so we know that angular momentum equals mass times speed times radius. So we would have that mass times speed 1 times radius equals mass times speed 2. Which would then give us the speed 2, so the speed after the object is released equals speed 1, so the speed as it's spinning times the radius that it's spinning at. However, as you might notice, this means that the speed that it's going at after it's released and the speed that it's spinning at are not the same. So when it's released, there would need to be a force to either accelerate it or decelerate it to this second speed. However, once it's released, there is no force acting on the object. I mean, there is air resistance and gravity, but for this demonstration, we are ignoring those and pretending they do not exist, since we're just looking at planar motion in horizontally, not vertically. So we can conclude that the conservation of angular momentum does not apply in this case. So now, if you look here, here's the proof that the distance traveled, so the total distance that the ball travels versus time, is constant. There is no change. If it was to abide by the conservation of angular and linear momentum, at some point here near the end, we would see that the velocity changes drastically to account for the radius term in the angular momentum equation. However, that doesn't happen. It just continues going at a constant speed. So now let's transition and look at a case that does obey the conservation of angular momentum. So here is the second example, and let's just look at it real quick. So as you can see, what happens is the object is spinning around and round with some angular momentum, and then I stick a screwdriver in between into the string, and suddenly the radius of the rotation changes, and as such the angular velocity of the rotation is also going to change. So now let's go back to the slides and let's look at that. Right, so here we have our diagram as usual, and as always we know that the angular momentum equals, well, this is a slightly different form of it, but mass times omega times radius squared. Just appreciate that omega times r is the speed that the object is spinning at, and so if we just separate that term, we get an r squared and an omega. So since the angular momentum is conserved, the angular momentum at the beginning of the motion has to equal the angular momentum after the motion. So then we have this equation, which is too long for me to say, but basically it says angular momentum at the beginning equals the angular momentum at the end of the motion. So then if we simplify this equation, we get that omega 2, so the angular momentum after the action happens, equals omega 1, or the angular momentum, or the angular velocity, sorry, before the action, times r1 over r2 squared. So you can see that depending on the ratio of r1 and r2, omega 2 is either going to be bigger or smaller than omega 1. And in this case, since the radius gets smaller, omega 2 is going to be larger than omega 1. And that makes sense since, as we know, our angular momentum depends on the mass moment of inertia. And if we lower the radius of the rotation, the mass moment of inertia also gets lower. So if the mass moment of inertia gets lower, the angular velocity has to increase in order to compensate and keep the angular momentum the same. So if we look at this next graph, you can see this is angle versus time. So the derivative, or the slope of the graph, represents the angular velocity. Therefore, you can see at the beginning here, the slope is somewhat mellow, and then suddenly it gets steeper. And this is because this is where the screwdriver hits the string, and that is where the sudden change in radius happens, and therefore there is a sudden change in angular velocity. Now, unlike last time where we said, oh well, we can't have a sudden change in velocity because there is no force to make that change in velocity happen. This time there is no change in velocity. This is a change in angular velocity. The actual velocity, or rather speed, I'm using those terms interchangeably here, but the speed stays the same. And you can see that in this graph. The speed stays constant. There's a few outliers down here, but those are pretty close and are may not be caused by it may not be there in reality, could be caused by, some tracks being slightly off or anything really. The main thing is that most of the dots here are on the same line that you can see there. And therefore you can see that the speed is constant. So there doesn't have to be an acceleration to make the change in speed happen. So I hope that you found that helpful and that it cleared up angular momentum, at least a little bit for you. And yeah, have a great day. Goodbye.